I'm going to show two ways to determine electron configuration as well as how to use noble gas configuration. So the first part, we're going to take a look at this chart, and you can see that the chart lists all of the different levels of orbitals. It organizes it left to right and top to bottom. So at the top we have 1s, and then underneath it 2s, and then 2p, and then 3s, 3p, 3d. And so on. And then over here, we need to remember, always need to kind of remember exactly how many electrons each can fill. So the s orbitals can fill up to 2, p up to 6, d up to 10, and f up to 14. So as an example, let's take a look at potassium. So now let's say we're going to write the electron configuration for potassium that has 19 electrons in its neutral state. And to use this chart, we're not going to go left to right or up and down. We're going to go diagonally. And so we're going to go in this direction, and that is going to give us the correct order that the electrons fill the orbitals. So the first it will fill is the 1s, and that's going to fill it. So that's going to be 2, right? Because we know that it has 2 electrons to fill it. And then the next one is 2s, and that's going to, I should draw that. That's going to be 2s, and that's going to fill it, right? And then the next diagonal, it's going to go through 2p, and that's going to fill up to 6, remember? And then it continues to go through the diagonal, and that's a 3s, and that's going to be a 2. All right, so right now we have 2, 4, plus 6 is 10, plus 2 is 12, and then according to the chart, it's going to go to the 3p, and then that's a 6. All right, so that gives us 18. We're all the way up to 18 right now. So we just need one more. So we're at 4s. It can hold 2, but we only need 1. So this would be the electron configuration for potassium. And you can see how the chart is necessary because it goes from 4s, and then the d's do a funny thing. It drops. The d's appear, and it's one less level, and then it goes to the 4p and then the 5s. So that's the reason for the diagonal, right? Because when you get to the d orbital and then the higher energy levels, then it kind of gets mixed up a little bit. All right, so again, this is kind of a lot to draw and write out, especially when we get to the higher numbers. So there is a way to use the noble gases to create kind of a shortcut. So if we pull the periodic table up, we'll find krypton, and that's going to be here. Or I'm sorry, krypton, potassium. All right, so we're going to find potassium, and I guess I can put it back there. We're going to find potassium, and the rule is for the noble gas configuration, we are going to find the noble gas that is closest to the element that we're trying to figure out, which is potassium, and take the noble gas that is closest but has fewer electrons. So we're going to go backwards on the periodic table, and we're going to come here to argon, which is has 18. So argon 18. Okay. Now, since argon has 18, we know that this is argon's electron configuration, because this is where we had 18 electrons fill. So we can use the symbol for argon. We're going to put that in brackets, and that is going to represent all of these electrons. All of these numbers and letters are represented by the symbol of argon in brackets. So now this represents our 18. We just need one more to finish off our configuration, and we write the AR4S1. So this would be the noble gas electron configuration, and you can see how much of a shortcut that can be, right? Now the problem is, what if we have something and krypton is our noble gas that we need to figure out. Well, here, I just happen to have the argon electron configuration, and I can see right away it went from 3p6, right? So the problem becomes, how do I know what krypton fills? How do I know what xenon fills? That is why when we look on the chart, I have this color-coded here, right? These color-coded symbols represent the orbitals that the noble gases will fill. I didn't include helium because that only has 2, so it's not really a big deal to make a shortcut or not. But these symbols represent neon, so neon's electron configuration fills to the 2p, argon the 3p, krypton the 4p, xenon the 5p, radon the 6p. So as an example, if I was looking for, let's see, strontium, right, SR38, and again the rule is to find the closest one with fewer electrons. That's going to be krypton. That's going to be Kr, and krypton has 36, and so we just need 2 more. We know that krypton fills the 4p, so it went through here, 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 and we go through there. All right, we fill it, and that's krypton, and then we continue on to the 5s, right, and that's going to be 2 more, right, and that's going to equal the 38. Okay, so that's how you use the noble gas configuration along with the electron configuration chart. All right, now instead of using this chart, I think a far easier way is to simply just figure out a way to use the periodic table. So let me clear all of this, hide potassium, hide the chart because we don't need it any longer. Okay, so you can see that my periodic table is color-coded. And let me explain the color codes to you. So everything in light blue, that represents the s orbitals. And you can see that it has 2 columns. So anything in column 1 is going to be have S1. Anything in column 2 is going to be S2. All right, so this will have 1 electron in the s, and then beryllium is going to have 2 electrons in the s orbital. And then we go over to the orange. This is the p orbitals. And you can see that there are 6 going across, 1, 2, 3, 4, 5, and 6, right? And so those represent the 6 electrons that can fill that orbital. And then we have the d, all right? And d can contain 10. And lo and behold, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 columns. So 10 going across, each of them representing the electron that can fill the d. And then down here, in the periodic part of the periodic table that I cut off, those represent the f orbitals with 14. And so there are 14. If you have a periodic table handy, you should have 14 going across at the bottom there. And then I can number off the energy levels. 4, 5, 6, 7. All right, D does something strange. We'll talk about it when we get there. Right now, just let me give you a quick example. So if we were doing the electron configuration for titanium. Okay, so titanium has 22. So we can go through and write down the entire electron configuration, not by using the chart, by looking at all of the different levels, all the different orbitals identified on the periodic table from top to bottom. So it goes through 1s first, okay, and it fills both of them. That's the hydrogen and then the helium. So it fills 1s2. It's going to fill the next layer, and that's going to be the 2s, 2s2. and then over here, the 2p6, okay, 2p, 1, 2, 3, 4, 5, 6, and then it's going to go through the 3s2, and then it's going to go through the 3p6, and then it's going to go through the 4s2, and then finally it's going to go through. Now here, this is where the D's get a little tricky, but it's easy to remember that the D's are just one less energy level. So instead of this being 4D, this is actually 3D, and then 4D's down here, and then 5, and then 6. All right, so now when we look at it, it goes 4s2, right? 4s2, that's this part, and then it goes into the D's, but that's a 3D, and then 1 and 2. So it's 3D2. Okay, so this would be the electron configuration for titanium. But again, we can use noble gases. So noble gases, the closest one going backward is going to be argon, right? So it's going to be argon. All right, so it fills everything up to argon, and now we just draw or write down the rest of it. So this is going to be 4s2, and then this part is going to be 3d2, and this would be, these two would be the same thing. Okay, and we did that all just using periodic table. Okay, we can do one more. Let's do one more to make it clear. Let's do, I don't know. Let's do something bigger. Let's do gallium. Okay, so Ga31. Okay, so again, we could go through each one. 1s2, 2s2, 2p, but easily we'll just go right to the noble gases. So this is argon again, right? So we can argon, and then it goes through 4s2, and then 3, remember that's 3d, all right, 3d10, and then it goes back up to 4 here because it's not a D, it's P, so it's going to be 4p1. Okay, I know it's a little confusing, but if you do a few of those as practice, and you just have to make sure you remember that the D's are one less. Okay, and draw yourself out a chart and pick out a few and check it online, and you'll find that it's a real efficient and easy way.